All right, 6.3. Um, 6.3 or chapter 6 is exponential and logarithmic equations. Now, I know that you have a button on your calculator that says log. It has nothing to do with the lumber industry. It has everything to do with expressions that have a variable as an exponent. We have dealt with many kinds of exponents. We've dealt with positive exponents, negative exponents, zero exponents, whole number exponents, fractional exponents. The only kind of exponent that we haven't talked about is what if your exponent is a variable. Normally, the variable has been the base. We've graphed x squared and x cubed and all kinds of x's, but never x in the exponent. And that's what the exponential function is. Now, Test 4 is probably, I'm not saying to panic you, I'm saying to prepare you. It's the test which traditionally has the lowest average or maybe tied with test 1. I'm sorry, Harley. I just want you to know so you do all your homework. It's not that it's that difficult. It's less people have seen exponential and logarithmic functions than all the other stuff. All the other stuff, you probably saw it in high school. If you took advanced math, you've seen this before. But if you didn't take advanced math in high school, then this may be your first go round with exponential and logarithmic functions. And anytime you see for the first, anything you see for the first time is more difficult than something that you've seen before. Now, like I said, I don't say that to scare you. I say that to encourage you to really understand what we're saying here, not this little x goes here and this little number goes there, but think about what it means. And if you have any trouble, if there's anything you don't understand, come see me. I can fix it if you come see me Wednesday and say, hey, I don't get what you were talking about Monday. I can help you with that. But if you wait till the day before the test and come see me and say, I don't get chapter 6, I'm just going to say, so sorry. I can't reteach you chapter 6 in an hour. So make sure you don't let it build up. If there's anything you don't understand, ask me. I can explain things in different ways. All right, here's the definition of the exponential function. For any a greater than 0 and not equal to 1, the exponential function with base a is defined as f of x, that's just the name of the function, equals a to the x. The important thing here is that a is some constant. We don't know what it is. It may be 2, it may be 3, it may be 1,000, but a is some constant, and the restrictions we have are on that constant. That constant has to be positive and not equal to 1. The x is the variable. Domain, as always, refers to what you can let x be. This says you can let x be anything. There are no restrictions on x. The domain of the exponential function is all real numbers, or negative infinity to infinity. Now, let's talk about why we only want to use positive bases not equal to 1. What if we had f of x equals, let's say, 1 to the x? If x was 2, what would be the value of that expression? That's 1 squared, which is 1. If x is 3, then that would be x or 1 cubed, which was, I think I said the wrong thing. I meant if a is 1 and x is 3, then that's 1 cubed, which is still 1. In other words, and I did a bad job of explaining that, but if the base is 1, it doesn't matter what the power is. 1 to the anything is still 1. In other words, that function is 1. If you let a be 1, then the value of that function is 1 for any x. That's just the line y equals 1, or a horizontal line through 1 on the y-axis. That's just not a very interesting function. It always equals 1. And what about negative bases? If we let the base be, say, -2 and raise it to an even power, what's going to be true about our answer? A negative raised to an even. It's going to be positive, and a negative raised to an odd power is going to be negative. That graph is bouncing all over the place, negative, positive, negative, positive. And not only that, if the base was negative, there are some values of x we couldn't use. What if a was, let's say, -9, and x is a half? Because we said x could be anything. If x is a half, what does the exponent 1/2 mean? Square root. Can you take the square root of -9? You can't take the square root of any negative number. And that's why we have the restrictions. We're only going to deal with positive bases so that the domain can stay all real numbers and not equal to 1, because otherwise that's just the constant function y equals 1. So you need to understand those two restrictions. The first time we ever talk about a function that we haven't talked about before, we look at its graph. Or we look at the graph of the simplest kind of function in that category, and then we pretty much know what moves a graph left, right, up, or down. So if we can figure out what the simplest one looks like, then we can graph exponential functions that have been shifted. The simplest exponential function, the one you can deal with in your head, is y equals 2 to the x. That's the smallest base, smallest integer base. So you can probably raise 2 to powers in your head. I'm going to start down here at the bottom of my XY chart. I didn't know what this graph would look like, so I knew that 1 or 2 or even 3 ordered pairs wouldn't be enough to get a good graph of it. So I chose these 7 ordered, or these 7 x's, and I need to find the 7 y's that go with them. If I let x be 3, then this is 2 cubed, which is 8. And if x is 2, this is 2 squared, which is 4. And if x is 1, 2 to the first is 2. Ooh, what about if x is 0? What's 2 to the 0? Yes, remember, anything to the 0 is 1. What about 2 to the -1? What does that mean? That means take the reciprocal of the base. Whenever we see a negative exponent, we take the reciprocal of the base, which would be 1/2, and that makes the exponent positive. 1/2 to the first is just 1/2. What about 2 to the -2? That's 1 over 2 squared, or 1/4. And 2 to the -3 would be 1/8. And we could keep going forever to the left. 2 to the -4 is 1/16. 2 to the -5 is 1 over 32. We could go infinitely small or infinitely large because the domain of this function is -infinity to infinity. Let's graph these 7 ordered pairs and see if they give us a good idea of what this function looks like. For reasons that we'll talk about in just a minute, I'm going to call this point 0, 1 the critical point for this function. It's right here on the y-axis. It's the y-intercept. All right, going to the right from there, I have the ordered pair 1, 2, 2, 4, 3, 8. I don't even have enough tick marks for that. But certainly I can see that as my x's are getting bigger, my y's are getting big really fast. Think about powers of 2. I think scared would be the appropriate emotion when in about the 5th grade or so, my 5th grade daughter's teacher asked them to come up with how many times you would have to multiply 2 by itself to get to 1,000,000. And I thought that was kind of a scary thing for a 5th grader, maybe a 6th grader to do. I wasn't really thinking about it in terms of being an exponential function and how fast exponential functions get big. Think about powers of 2. You start out with 2 mice in the kitchen, the next day you have 4, next day you have 8, then the next day you have 16, 32, 64, 128, 256, 512. Gets big really fast. Mice and roaches increase exponentially. That's what the exponential function or the word exponential growth means when you see it referred to in terms of maybe the national debt, unfortunately, is growing like roaches, exponentially, getting big really fast. That's what the graph of the exponential function is showing us. As x's get big, the y's get big really fast. What about as x's get small? We have the ordered pair -1, 1/2. When x is -1, y is 1/2. Boy, I don't have much room between my tick marks there. When x is -2, y is 1/4. That's getting so darn close to the x-axis it's hard to graph. When x is -3, y is 1/8. What do you notice about those y's as x's get infinitely small? Okay, when you say infinitely smaller, that indicates at some point they're going to become negative. They approach 0, but there is no power of 2 that would give you a negative. Think about these fractions: 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. That's getting closer and closer to 0, but never going to be 0. What do we call that line? We've encountered it once before, very briefly. We graphed a function that had a line that it got closer and closer to, but didn't touch. If I remember the word for that line, starts with an A. Yes! You don't even have to show up for this test. You just got an A. I'm kidding. The line that this graph gets closer and closer to but does not touch is called the horizontal asymptote of the graph. I forgot I had typed this for you. This notation means as x approaches infinity, or as x gets infinitely big. What did we say the y's did? They get infinitely big even faster than the x's. As x's get infinitely big, y's get infinitely big. And this means as x gets infinitely small, y gets closer and closer to what? 0, but never becomes negative because there is no power of 2 that would give you a negative answer. And what's the equation of the x-axis? It's a horizontal line, so how does what equation gives you a horizontal line? That's when y equals a constant. And on the x-axis, what does y equal? All the points on the y or on the x-axis. The y is. No, I'm not talking about this graph just a minute. I'm talking about the equation of the x-axis. All the points on the x-axis, the y is 0 because you haven't gone up or down. The horizontal asymptote of the exponential function is y equals 0, also known as the x-axis, which you wouldn't write y equals x-axis for the equation of that line. You'd write y equals 0. So as x gets big, y gets big really fast. As x gets infinitely small, your y's get closer and closer to 0, but are they ever going to be 0? No matter how small the y gets, you can always chop it in half. You can chop it in half and then take one of those halves and chop it in half again. You're never going to run out and be 0. You're just going to get pieces that you have to have a microscope to see. All right. One other note about this graph. This point 0, 1, There's two reasons that I called it a critical point. And I forgot that I typed that. I already had that typed for you. The critical point is 0, 1 for two reasons. The first reason is that's where the graph really takes off and starts getting fast, or starts getting steep very quickly. The graph, it's not technically correct to say the slope of this curve, but if you'll let me say it anyway, the slope of this curve gets much steeper past that critical point. Another reason that I call it a critical point is because that point, 0, 1, is on the graph of any exponential function unless it's been shifted left, right, up, or down. All right. For example, if the base was 3, what's 3 to the 0? 1. If the base was 10, what's 10 to the 0? 1. If the base was 1/3, what's 1/3 to the 0? 1. What if the base was negative 1/3? Then it's not an exponential function because we've restricted the bases here to being positive. So it's critical because that's where the graph really changes shape, and that's on the graph of every exponential function regardless of the base. So maybe we can figure out real quickly what would move that graph to the left or to the right or up or down. Think about this. When we graphed the simplest quadratic function, y equals x squared, what was the shape of that graph? It's a parabola with vertex where? 0, 0. And if I added or subtracted something inside the parentheses before the squaring, how did that shift the graph? Opposite of the guy inside, because that's the horizontal shift, and the horizontal shift has always worked the opposite of what we expected. What's added or subtracted before you do the squaring, the cubing, the absolute valuing, whatever you're going to do, before you apply that function, what's added or subtracted is your horizontal shift. So remember that moves the graph to the right too. And what if we added or subtracted something after the function was applied, the squaring, the cubing, the whatever? What did that do to the graph? That was your vertical shift, and it worked like you would expect. Subtracting 3 moved the graph down 3. You can apply what you know about horizontal and vertical shifts to the exponential function and figure out the graphs of many other exponential functions. For example, my example B here, y equals 2 to the x minus 3. If I ask you to evaluate that expression for, say, let's at x be 5, if I ask you to let x be 5, would you do the subtraction or the exponentiation first? You'd say 5 minus 3 is 2, and then you'd do the squaring. So in other words, that 3 is subtracted before the function is applied. What does that mean about how it shifts the graph? Horizontally, the opposite of, it's not guy in parentheses now, it's the guy in the air. And that's so mathematically imprecise that it almost embarrasses me, but it works. All right?
Physics. There's a man in the air, apparently.
What?
You just said the man in the air.
The guy. I didn't say the man, the guy. The guy can be a girl, a guy, a variable, a number. Guy is your catch-all noun. All right. So this -3 subtracted from x before you do the exponentiation, that's a horizontal shift. And what way do you think it's going to be shifted horizontally, left or right? The horizontal shift has always been the opposite of what we might have guessed. So this actually moves the graph to the right 3. Now, if I started at that critical point, 0, 1, the usual critical point for the exponential function, and counted to the right 3, what would be the ordered pair that names that point? 3, 1. Shifting a horizontal shift affects the x-coordinate. You can add that 3 to the 0, and the critical point is now 3, 1 instead of 0, 1. You can get that point 2 different ways. You can either put your pin on 0, 1 and count to the right 3, or you could say a horizontal shift is going to move the x-coordinate 3 units to the right. It's not going to do anything to the y-coordinate. So the critical point is now right here. And does that affect the horizontal asymptote? If you move this whole graph to the right, will it change the horizontal asymptote? You can move the x-axis left and right all day long, and it's still the x-axis. That's why I said the horizontal asymptote is still y equals 0. Everything else about this graph is the same as the previous graph, except for that critical point being shifted 3 places to the right, or the whole graph being shifted 3 places to the right. That's still the place where the steepness of the graph changes dramatically. That was the next thing I was going to say. To get this right on the test, you have to know 3 things, and you need to show me those 3 things. Number 1, you need the critical point. Number 2, you need the horizontal asymptote. And number 3, from there, you just need to know the right shape. If you attach the right shape going through that critical point and whatever the horizontal asymptote is, that's as precise as I'm looking for. It'll keep us from having to make these huge XY tables. What about my example C? If I told you to evaluate that expression for x equals 2, what would you do first, the exponentiation or the subtraction? Oh yeah? If I said let x be 2, you'd say 2 minus 3 and then... No, you would do the 2 squared and then subtract 3. So that 3 is subtracted after the exponentiation, which makes it which shift? Vertical shift, down 3. That vertical shift has always worked like we expected it to. If I put my pin on this critical point 0, 1, and then move it down 3, 1, 2, 3, what's the name of this point? 0, negative 2. You could put your pin on the old critical point and then count down 3, or you could say a vertical shift is going to change the y-coordinate. Just subtract the 3 from the 1, and you get negative 2. So here's our new critical point, 0, negative 2. What about the horizontal asymptote? If the rest of the graph is shifted down 3, is that going to affect the horizontal asymptote? It has to go with the rest of the graph. So it was 0. If you shift that down 3, where is the horizontal asymptote now? No, it was at 0, and then count down 3. It's now at negative 3. In other words, that constant on the end gives you your horizontal asymptote. And if there is no constant on the end, then the horizontal asymptote is 0. Oh, yeah. Yes, sir.
Then why on B?
We did move it horizontally. We didn't move it vertically because there was no constant added after the exponentiation.
So you're only going to have to change that
after. What's What's added or subtracted in the exponent is your horizontal shift. What's added or subtracted after the exponentiation, that's your vertical shift.
So only y changes effect.
Hold on, I gotta sneeze. That'll sound good on video. All right. Caleb, I'm not positive I understand what you just said. Is it clear in your head, or you want to say it for me one more time?
Only y changes will affect the horizontal.
Let's say only vertical shifts. Only vertical shifts will affect the horizontal asymptote. It doesn't really make sense to say only y changes. Every time you change the x, the y changes. All right. I have my critical point. I have my horizontal asymptote, and I know the general shape of the exponential function. I can get pretty fast at graphing these exponential functions now. I just thought of something I want to show you on a calculator. The TI 83 or 84 that you have to have for pre-calculus and business calculus, I think I've convinced my pre-calculus class that it's a wonderful tool. But if you don't know what you're supposed to know about the function before you graph it on a graphing calculator, you're not going to interpret the graph correctly. Let's see. Go away. Oh, I remember there's a problem with this I need to fix. Y equals 2 to the x minus 3. No, we're graphing 2 to the x minus 3. That looks better than I thought, but it doesn't really flatline to the left. The graph is approaching a horizontal asymptote, and unless you know to type it in, unless you tell the calculator, hey, the horizontal asymptote is -3, the calculator's not going to graph that for you. What I've seen a lot of folks turn in as graphs on the test is a graph that looks like it just stops right there. It doesn't stop right there. It goes forever to the left, just getting so close to the horizontal asymptote that it's hard to show that on a graphing calculator. It's easy to show that on paper. It's easier to show that than on a graphing calculator. So make sure, and I know I have this typed somewhere, right here. To receive full credit on your homework and your test, you must graph the horizontal asymptote. You must show me that you know that graph has a horizontal asymptote and you know what it is. Otherwise, you're just copying down something off your calculator.
So we have to graph that line together.
That's the horizontal asymptote. It doesn't go through the critical point, it's just below the critical point. All right, so example D has both a horizontal shift and a vertical shift. Which one of those numbers is giving you your horizontal shift? The one that's added in the exponent before the exponentiation is done. That actually shifts the graph how? To the left one, because that horizontal shift has always worked the opposite of what we might have guessed. And what about that 2 on the end? What does it do to the graph? Shifts it up 2. Now I could put my pen on the point 0, 1 and count to the left 1 and up 2. I will check my answer that way. But tell me this, if I started at 0, 1 and shifted to the left 1, start at 0 and shift to the left 1, what does my x coordinate become? Negative 1. And then if I start at the y coordinate 1 and shift it up 2, what does it become? Yeah, start at 1, count up 2, y is 3. Let's do it the other way and see if we get the same thing. Start at 0, 1, count to the left 1 and up 2. Sure enough, I would be at the point negative 1, 3. Now, what's affecting this asymptote? Moving it to the left 1 or up 2? The vertical shift is going to shift that asymptote. The asymptote was at 0. If you shift that up 2, now it's at 2. I could make up an example where that's not true, but it's not going to happen to you in college algebra. So for your purposes, yes, but not really. Graph that horizontal asymptote so I can see that you know the graph doesn't keep going forever and somewhere down here become negative. Yep, because we're not going for a great level of precision. We have a graphing calculator for that if you go on to pre-calculus or calculus. You just need to know enough to interpret what your calculator shows you, because if your window is set some wonky way, the graph may not even show up. You've got to know, hey, I know what that's supposed to look like. Something's wrong. Let me make some changes. All right, example E. Y equals negative 2 to the x. Oh, that's exactly what I was thinking. I thought we could not, or we're not going to use negative bases. My question is that base negative?
Well, it's already
No, that's not. I'm not asking is the y value negative. I'm asking you is the base negative. Does that mean raise negative 2 to a power? The answer is no. Okay, but now you have to tell me why. Remember the difference? Ooh, this is first day of class. Real blast from the past. Remember the difference between these two guys? I wrote you a big note first day of class that said, when you raise negatives to a power, you have to pay attention to parentheses. You have to realize that if the negative is inside parentheses, it's part of the base. This means negative 5 times negative 5, and that is positive 25. But that's not what this means. Without parentheses, the negative is not part of the base. A way that you could write that would help you understand it better is negative 1 times 5 squared. And that's why that answer is negative 25 instead of positive 25. So going back to example E, is that negative part of the base? How do you know? Not inside parentheses, it's not part of the base. That's negative 1 times 2 to the x. So is that base negative? No. Have we violated our definition? Nope, that's fine. What did it do to our good old quadratic graph, our parabola, if we put a negative exponent on it? flipped it upside down, reflected it with respect to the x-axis. Guess what a negative exponent's going to do to this graph? Same thing. Instead of the critical point being 0, positive 1, if you reflected that with respect to the x-axis, it would be 0, negative 1. This negative coefficient reflects graph. WRT is with respect to the x-axis. So if you can imagine our original graph, I dotted it in very lightly right there. If you can imagine that graph flipped over the x-axis, that's the graph of y equals negative 2 to the x. And it doesn't look that wobbly when I'm not zoomed in that much. It's a nice smooth graph approaching the x-axis. But from below, rather, oh, that's just getting worse. Now it looks good. All right. Looks good. Looks good to me. One more. Part F. Y equals 2 to the negative x. What does that negative exponent, what word pops in your head when you see a negative exponent? Reciprocal. Good job. That was months ago I said that. Oh, I hypnotized you. That's why it's still there. I remember. Whenever you see a negative exponent, the word reciprocal is supposed to pop in your head. Taking the reciprocal of the base makes the exponent positive. So how could I rewrite that with a positive exponent? I don't take the reciprocal of the exponent, I take the reciprocal of the base. Man, you are just all over it today. 1/2 to the x. Taking the reciprocal of the base makes the exponent positive. I'm not sure how that changes the graph, though. Whenever you're not sure, you can always, for any of these first 5 examples, you can make an XY chart. If you had to. The goal is to not have to, but if you have to, you can. So let's see. Let's raise 1/2 to these powers, and it's a little bit easier to start at the bottom and go up. So if I let x be 2, what is 1/2 squared? 1/4. What is 1/2 to the first? 1/2. And 1/2 to the 0? Anything to the 0 is 1. And 1/2 to the negative 2? I'm sorry, I skipped 1. 1/2 to the negative 1? Huh? You may be right. I just couldn't hear you. 1/2 to the negative 1. What would that be? 2. Good job. You flip the 1/2 and you get 2. And 1/2 to the negative 2. Again, you flip the 1/2. It becomes 2. And now it's to the positive 2. It's just 2 squared is 4. Plot those 5 ordered pairs and see what has happened to your graph. -2, 4, -1, 2. Same critical point, 0, 1. It wasn't shifted left, right, up, or down. 1, 1/2, 2, 1/4. And I expect from there it's just going to get closer and closer to the x-axis. But as x's increase, your asymptote is still x equals 0. Y equals 0. Gosh darn it, yes. I cannot say the word asymptote without thinking about MC Hammer. For as long as I live, I'll probably never see the word asymptote without thinking, you can't touch this. I'm going to put it on a t-shirt. With a parachute pants. First time I went out on with my husband, he had on a pair of parachute pants. That was 1981. And you weren't born yet, most of you. We weren't in Crossville. We were in Lawrence County, Alabama. Explains a lot. Oh my gosh. In the 6th grade. Yes, they were. Yes, they were. All right. Yeah. Really, it's corny, but it'll help you remember the word. Horizontal asymptote. I can't even say it again. It's so silly. You can't touch that. You can get closer to it. You can get infinitely close to it, but you can't touch that. I'm sorry. What did you say? All right. See, it works. It works. A lot of corny things work in math. Okay, so here's what we just discovered. And I remembered this time that I've already typed it for you. If the base is greater than 1, like 2 to the x, any base greater than 1, your function is going to be increasing and getting big really fast. 3 to the x, 10 to the x. Think how fast 10 to the x would get big. 10 to the first is just 10, but 10 squared, y is already 100. 10 cubed, y is 1,000. 10 to the 4th, y is 10,000. The bigger the base, the steeper the graph is. But if you have a base between 0 and 1, like 1/2, then the graph is decreasing. It's getting lower from left to right. Still approaches the x-axis. Y's are never going to be negative, but it is getting smaller as x's get bigger. All right. Any questions so far? If you have any trouble with this on the homework, you come see me. I don't know why. Maybe it's the air in my office or what, but things seem easier in my office. Really, it's sitting down with me one-on-one. I can make things more clear than I can to a group of 20. So if you have any trouble, come see me. I'll be glad to help you with it. Next big thing in 6.3, Roman numeral 2, the second most famous irrational number in the world. The first most famous irrational number in the world is pi, 3.1417, goes on and on and on, without ever terminating or forming a repeating pattern. So it's really, really cool. The second most famous irrational number in the world is E, and it's approximately 2.71828, but it goes on and on forever without terminating or forming a repeating pattern as well. Now, pi comes from dividing any circle in the whole wide world. If you divide its circumference by its diameter, you get about 3.1. All right? That's where pi comes from. It's not quite as easy to say where E comes from, but I have a chart from the book that kind of, the real definition is from calculus. That's why I can't really tell you where it comes from until you take calculus. But this example, this is page 429 in the book. And this formula in the right-hand column of this chart is the compound interest formula. We're going to talk about that later. If we invested $1 at 100% interest, compounded once a year for 1 year, what would $1 at 100% simple interest become in 1 year? It would become $2. 100% interest just doubles your money if it's simple interest. And then the more times your money is compounded per year, the faster your investment or your investment's the best word, the faster your investment grows. Let me tell you why that is. It's going to be important later. If you have an investment, or let's say a savings account where your money is compounded twice a year, then the second half of the year, not only do you earn interest on your dollar, but you earn interest on your previous 6 months' interest. That's what compound interest is. You're being paid interest on your interest. Or it works the other way too. On a loan, compound interest on a loan, you're paying not only interest on the amount you borrowed, but you're paying interest on other interest that you've accumulated unless you pay that off every month. So the more times your money is compounded per year, and that's what N stands for in this formula, number of times compounded per year, the faster your money grows. If you had $1 in the bank at 100% interest compounded twice a year, then at the end of the year you'd have $2.25. If your money was compounded 5 times a year, then at the end of the year you'd have about, well, the bank would round it up to $2.49. If your money was compounded 10 times a year, the bank would round it to $2.59. It's increasing, right? The more times our money's compounded per year, the more money we have in the bank at the end of the year. So far, so good. But what about 100 years? The bank would round it to what? Oh, wait. I said the wrong thing. I didn't mean 100 years. I meant 100 times a year. The bank would round it to $2.70. If we found an investment that compounded our money 1,000 times a year, that's about 3 times a day, the bank would round our money at the end of the year to what? $2.72. What if we had an investment that compounded our interest every 10,000 times a year? What would the bank round the money to at the end of the year? Still $2.72. Even if our money was compounded 100,000 times a year, at the end of the year, the bank's going to give us $2.72. Even 1,000,000 times a year, it's still not quite $2.72. These digits to the right of the decimal keep getting bigger and bigger, but it's never going to quite ever come out to 2.72. It'll be rounded up to 2.72, but that number just keeps increasing in the tenths, hundredths, thousandths, 10,000ths, millionths place, just like pi, no matter, how many decimal places you round it to, it'll never quite be 3.2. This number will never become 2.72. It just gets closer and closer to it. That's the magic number. That's darn close to the magic number that we call E. Just like we use, when we see pi, we don't freak out anymore. We might have in 3rd grade, 4th grade. But when we see pi, we don't freak out. We go, it's about 3.14. That's what you have to do when you see E. Fight any urge to run that you have and go, it's about $2.72. I can be precise as you want me to, but it's about 2.72, 2.718. All right. And that documentary last night had some good applications of E. I should have recorded it and brought them to you. It was fabulous. Well, he recorded it when I wasn't there, but he watches Discovery Channel all the time. Discovery and History. Yeah. We don't watch much ABC, NBC, CBS. All right. So, e to the first, rounded to 2 decimal places. Let's say 3 decimal places. What's e to the first rounded to 3 decimal places? Yeah, 2.718. That's approximately what e is. Now, before you grab your calculator, let's try to get a good guess for what this would be. What does e to the negative 1 mean with a positive exponent? 1 over e. If you're not panicking and you see 1 over e, you'll go, not quite 3, right? E is not quite 3, so e to the negative 1, or 1 over e, is darn close to 1/3. Punch it on your calculator and see how close. Everybody in here may have a different calculator, but just use your exponent key, which either is a caret or says y to the x. Look for your E button. It's right over a button that says LN, and we'll figure out what that LN is later. Darn close to 0.36. You said it would round to 0.368. Okay. Yes, everybody has an E button. It's right over your LN. You will either have to press shift or second to get to it. So if you don't see your E button or you don't know how to enter an exponent, wave at me. Please let me come see you, because you need to know how to do that for tonight's homework. Do you see it, Abigail? E is right over natural log. Natural log's right there. And then, since it's in yellow, second and E. Oh, you know what? It's time we have this discussion. For the next 4 weeks, for the rest of the semester, you need to bring your calculator every day. Because even though everyone in here may have a different calculator, they all fall into one of 2 categories. And here are the categories: the fabulous frontwards calculator and the cursed backwards calculator. You have the cursed backwards calculator. As long as you learn to use it, it's fine. That's what I got a master's degree with. But the fabulous frontwards calculator, you can enter the E and then the negative 1. The cursed backwards calculator, you have to enter the negative 1 and then that E button. All right, so enter the negative 1 and then second and that. Yep. So everything we do the rest of the semester, you're going to do the same thing, but backwards. And it's going to be okay. Whichever calculator you get used to, it'll be all right. But bring it with you every day, because we're going to learn some new buttons and we're going to punch some ugly expressions. And before the test, you need to be sure that you know how your calculator works. Don't do all your homework with one calculator and then borrow a different calculator for the test. That will not be good. All right. Before we grab a calculator, let's guess what E cubed would be close to. E is about what to the nearest whole number? To the nearest whole number, so I can do it. It's no E. E's darn close to 3. What's 3 cubed? 27. So this is going to be close to 27, but less than 27, because E is not quite 3. Punch it on the calculator and round it to 3 decimal places for me. 20.085. Does anybody second that? Oh, rounds up to 0.086. Okay. Kind of close to 27. And the cursed backwards calculator, you're going to enter the 3 and then the E button. Is anybody having any trouble getting that 20.086? Because I want to show you right now so you can do the homework well. Everybody's got it. All right. The moral of this 4th example, frontwards calculator, folks, listen to me first. If you have the fabulous frontwards calculator, you enter this exactly like it looks, left to right, your E, then open a parentheses, then 0.347 times 6, close parentheses, and then hit enter. That's going to be somewhere around 9, 8. Is that what you're saying, Harley? All right. My cursed backwards calculator, folks, it's going to be okay. You're going to get used to it. You just enter the parentheses first. Parentheses, 0.347 times 6. As soon as you hit close parentheses, your calculator will do the multiplication for you, and then you can do second and E. See, it's whatever you get used to. All right. You have to use parentheses judiciously. When you need them, you have to enter them. What about the graph of y equals e to the x? If we let x be 0, what is e to the 0? Anything to the 0 is 1. So this graph has the same critical point, 0, 1. It's horizontal asymptote. No matter what power you raise e to, you're never going to get a negative because e is a positive number. So the graph's going to keep approaching the x-axis to the left, just like all the other exponential functions with bases greater than 1. It's an increasing function. It hits that critical point 0, 1. And then what did I say a while ago? The bigger the base, the what? Steeper the function. 3 to the x is going to be a little steeper than 2 to the x. Guess where e to the x is? Right between them. A little bit closer to 3 to the x than 2 to the x. E's a little bit closer to 3 than it is 2. So the graph of e to the x is going to be right between those two graphs, just a little closer to 3 to the x than 2 to the x. Everything else is the same. Same critical point, same horizontal asymptote. Horizontal shifts, vertical shifts, reflections, all would work the same way they did on every function we've talked about this semester. What, Kevin? So far, so good? So let's graph one that has been shifted. Y equals e to the x minus 3 minus 1. How do you think subtracting 3 from the x before you do the exponentiation affects the graph? To the right, 3. If the critical point originally had the x-coordinate 0 and you moved it 3 places to the right, what would the x-coordinate become? Yeah, just add 3 to 0, you get 3. What does this subtracting 1 after the exponentiation is done do to the graph? Down 1. So if the y-coordinate of the critical point had been 1 and you shifted it down 1, where would it be now? 0. Let's just put our pin on 0, 1 and go to the right 3 and down 1. Is that the same thing we got for the critical point? Yep, 3, 0. If the rest of the graph is shifted vertically, then the horizontal asymptote is going to be shifted vertically. Where was it originally? Y equals 0, so where is it now? Y equals negative 1. Oops, I already typed Y equals. Kind of shallow up to that critical point, but at that critical point really takes off steeply. the amazing thing about that number E is it happens. In real life, it happens. In biology, if you're talking about the growth in bacteria in a Petri dish, if you're talking, my husband is a biologist for TWRA. If he's talking about the growth of the wild hog population on Catoosa, that equation is going to have an E in it. That's the rate at which populations seem to increase or decrease. And that's pretty amazing to me when things that you thought people just made up, God knew about it long time ago. It's always been there. We just now found it. So that's what I like. One of the many things I like about math. The other thing I like about math is there's always a right answer. And that's not always true in psychology. So I like math better. All right. Let's see if we can talk about these exponential equations real quickly and get through with these examples so that you can finish the homework tonight. Solving exponential equations. Exponential equations are just equations which have exponential expressions, and an exponential expression is an expression where the variable is the exponent. Think about it. If this is maybe base 3, if I had 3 to the x equals 3 to the y, the only way that could be true is if x and y were the same thing. Or if I had 10 to the x equals 10 to the y. The only way that could be true is if x and y are the same thing. That gives us a tool for solving exponential equations. Only some of them, but the ones that fit this pattern are pretty easy to solve. If we can write both sides as having the same base, then we know that their exponents have to be equal. You can just take the bases off and set the exponents equal to each other. For example, let's see, this is page 433, I think. Start with the easiest one, 58. If 5 to the x equals 5 to the negative 6, what does x have to be? Negative 6. Well, that one was pretty easy. They do get a little bit more complicated than that, but if 5 to the x equals 5 to the negative 6, the only possible way that that can be true is for x to be negative 6. Number 60. 3 to the negative x equals 81. Now this one's just a tiny bit harder. I can't think of the number which, if I take the opposite of it and then raise 3 to that power, it'll give me 81. Maybe I could if I squinted really hard, but I have enough squint lines on my forehead. So I recognize 81, just because I've done it a bunch, I recognize 81 as a power of 3. How many times would you have to multiply 3 times itself to get 81? 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So in other words, I can write that 81 as 3 to the 4th. I didn't do anything to the left-hand side, or to the left-hand side. I just wrote the right-hand side as 3 to the 4th. Now I can tell you what x would have to be in order for this left-hand side to equal the right-hand side. Can you tell me? If negative x equals 4, then x would have to be negative 4. And if you figured that out without writing anything down, fabulous. Negative 4 is the right answer. If you need to write this down to solve the equation, that's fine too. Just set the exponents equal to each other, solve for x. You'd have to divide both sides by -1. And that's how some folks got -4 in their head. Is that okay, Harley? Okay. All right. Moving up one more level of, I'm not even sure this is harder. Number 64, 5 to the x plus 5 equals 1/5. Now, when I said that this tool can only be used to solve some exponential equations, let me clarify that. The tool of just taking off the bases and setting the exponents equal to each other only comes in handy if you can write both sides as having the same base. On number 60, if 81 had not been a power of 3, then I would have to figure out a different way to solve this, and I will in 5.6. But right now, we can only solve equations that you can write both sides having the same base. If I know that's my goal on number 64, what base do you think would be simplest to use, base 5 or base 1/5? I like to make things as simple as possible. I already can count by powers of 5 better than I can count by powers of 1/5, so this is the one I want to change. How can I write 1/5 as 5 to the something? 1/5 is 5 to the -1. I'm not doing anything to the left-hand side. I'm just rewriting 1/5 so that it has the same base. Because once it does have the same base, I can take the bases off and solve for x. All right, I'm going to try to do 3 more real fast. Number 68. It may take just a little bit of practice, but you'll learn to recognize that 9 and 27 are both powers of what? 3. All right, 27 is not a power of 9. 9 squared gives you 81. 9 cubed gives you 729. So they're not both base 9. They're both base 3. How could I write the 9 as base 3? 3 squared. Let me put that in parentheses, and I'll tell you why in just a second. What about the 27? How can I write it as base 3? Yep. I'm going to put that in parentheses as well. All I've done is make the substitution. 9 is the same thing as 3 squared, and 27 is the same thing as 3 cubed. But as long as those parentheses are there, this is still base 9, and that's still base 27. How would I remove those parentheses? When I raise a power to a power, what do I do with the exponents? You multiply them. So 2 times negative x plus 15, make sure you distribute that 2 completely, would be negative 2x plus 30. And the right-hand side, when you raise a power to a power, you multiply them. That would give you the exponent 3x. You can't remove the bases until you've removed the parentheses and you have the bases being the same. This was still base 9, this was still base 27, but now they're both base 3. Now I can take the bases off and say negative 2x plus 30 has to be the same thing as 3x, and solve that equation. Add 2x to both sides and divide by 5. Any questions? All right. One more equation and one word problem. 76. Just when you thought it was safe to go back in the water. Do you have to be over 40 to get that reference? You got it? Megan, what is it? Jaws. Right, just when you thought it was safe to go back in the water. Jaws 2. I like that you knew that, Megan. All right, number 76. Whenever we see an E, we're going to take a deep breath and go, it's just 3. Play like it's just 3. If I could do it with a 3, I can do it with an E. It's the same thing. Not really, but darn close. All right, I already have base E, except for I need to get rid of these parentheses. When I raise a power to a power, I multiply the exponent. So this first factor is just what? Without the parentheses. E to the 4x. That's all I'm going to do in that step. Now, I've been saying when both sides have the same base, you can take off the bases. I left something out of that sentence. One word, one important word. When both sides are a single exponential expression with the same base, you can take off the bases. I don't have a single exponential expression here yet, but I do know when I multiply two expressions that have the same base, what can I do to their exponents? You add them. That's day 1 of college algebra 2. When you multiply two expressions with the same base, you add their exponents. Now you have both sides being a single exponential expression. You can take the bases off, and what kind of equation do you have? It's the first one of these we've run into today. Did you say it, Courtney? No. What kind of equation? Quadratic equation. And what's the first thing you have to do in solving a quadratic equation? Get it in standard form. If you start factoring before you're in standard form, that's not going to be good. Now you can solve that by factoring. You'll get x plus 6 times x minus 2. This just reminded me of something that folks missed on the test, and it just killed me, just broke my heart. You had, shoot, can I show you real quickly? The problem number 5, you were graphing f of x equals x times 3x minus 8 squared times x minus 1. The first thing you had to do, well, you gave me the end behavior and then the y-intercept, and then you gave me the x-intercepts. Everybody had 1, I think. A lot of folks didn't have 0, but you should have had 0 as an x-intercept. The thing that killed me, whoop, that will kill me. That will get me fired. X equals 1. The thing that killed me, I think only one person, maybe 2, but I think only 1, set 3x minus 8 equal to 0 and got 8/3. I don't know. I wish I knew what you were thinking. I wish I'd known before the test what you were thinking and how you found your x-intercepts. But you find x-intercepts by setting each factor equal to 0. And when you set that equal to 0, a lot of people just had 8. It wouldn't be 8, it'd be 8/3. So here, when you set each factor equal to 0, you get -6, +2, and that's your 2 solutions. All right, the only thing that I did not have time to do, it sounds like a scary thing for me to leave out because it's a word problem, But the thing is, it's a problem that has words in it, but really it's just they give you an equation, they tell you a number to put in the place of the variable, and it's a calculator problem. If they say number 96, a formula for atmospheric pressure, find the atmospheric pressure at a height of 2 kilometers, that's just put 2 in place of h and punch it on the calculator. So it's not the kind of word problem you have to come up with the equation. If you want to hang around and make sure you can punch it, I'll hang around with you, but it's just put a number and punch it. All right? Go ahead and try to punch that if you want to. Those of you who want to make sure you can get the right answer before you leave.
I really wish you were my manager at Walmart and you'd say that.
Let H be 2. My fabulous frontwards calculator, folks, can just punch it left to right. Make sure you use parentheses. If you have a frontwards calculator, it's 760 times E to the, and you have to have that exponent in parentheses. Parentheses, negative 0.145 times 2, close parentheses, hit equals. What did you get? And I'll see if it's, that sounds about right, 568, because as the altitude increases, the air pressure decreases.
Your conference is scheduled to end in 2 minutes.
When this Bluetooth lady starts yelling in my ear, it startles me. Miss Abigail, my lovely backwards calculator person, did you get the 568, or can I write down the buttons for you? Okay, I'm going to show you. Let me write this down for you, and then Miss Courtney, I'll answer your question. Fabulous backwards. Yeah, go away. She's got the fabulous the cursed backwards calculator. Miss Abigail, this is exactly what you're going to enter. Parentheses, negative point. Is that 145 or 345? I think it's 145. That's exactly your keystrokes.